So in this little video, I'm going to just review some of the examples that were done in class in case you missed it or you need to go over it again. So first of all, just to recap, Q is also known as trial KSP in this case. So it's the same value or the reaction quotient that we've been looking for all along. So what we're going to be looking at here is we want to look at the actual concentrations of the reactants. We want to know if a precipitate forms. So to do that, your solubility guidelines aren't quite enough. What we need to do is to compare Q, which is your reaction quotient at any point, to the real KSP that you're going to look up in some tabulated data that you can find on page 725 and 726 of your textbook. So just to recap, what you're looking for is a comparison between Q and the real KSP, that's the table value. If you calculate your Q, or your trial KSP, to be less than that tabulated value, you'll find that your solution is actually unsaturated. That means you can keep dissolving stuff into it, and therefore no precipitate will form. So if Q is less, you're going to have no precipitate. If it's greater than your real KSP that you looked up in the tables, you will get a precipitate, because what that means is that you are supersaturated. You went so far towards the products that nothing more can be dissolved. So you'll definitely get a precipitate there. If Q happens to be exactly the same as your real KSP, you're not going to get any precipitate because you're exactly at saturation. So that means nothing has actually come out of solution. It is all dissolved, but just barely. Example number 1. In this case, a student is mixing 20 milliliters of a calcium chloride solution with 20 milliliters of a sodium sulfate solution. What you're being asked is there precipitate form? Well, the very first step that you have to consider is the balanced chemical equation. You need to be able to do a double displacement and determine which one might actually precipitate. So there's no guarantee. Just using your solubility tables, you'll see that you'll have a little star showing that calcium sulfate may be slightly soluble. So in that case, it's sparingly. We don't know for sure whether it will actually precipitate, whether it will be completely dissolved or they'll be supersaturated, and therefore you'll see some of this solid. So what we need to do is we need to start by looking up the KSP value from your tables. So go to page 725 in your textbook, or 726, and you're going to look up the KSP value for that calcium sulfate, which is your solid or your possible precipitate. So if you look that up, you'll find 7.1 times 10 to the negative 5. Note that it's a very small number. -5 is fairly high for an exponent in the low areas. And what you need to think about there is that that means it's probably not that soluble, but we need to know will precipitate. So we need to figure out the net ionic equation. So looking back at your balanced equation, considering calcium sulfate is the possible precipitate, you're going to show the dissociation of that. You're going to have at the beginning your solid showing the dissociation. Don't forget your double arrow. Now this is a 1-to-1 ratio, so the coefficients for calcium and sulfate ions are 1 and 1. Now, once we do that, what you need to remember is that we are mixing 20 milliliters with 20 milliliters. So that means we have a new total volume of 40 milliliters. So we've taken these two ions and they're no longer in their original 20. They're floating around in this big vat of, okay, it's not that big, but 40 milliliters. So it's twice as much solvent than they had before. So to find the new concentrations, we need to consider that our new total volume is 40 milliliters or 0.04 liters. Now, when we did dilutions, we knew that the initial concentration times volume will equal the final because the number of moles doesn't change. Or in this case, then the concentration of the ions will change because our volume has changed. So, calcium, what we're going to look at, we want to know the new concentration. So we're going to multiply the initial concentration and the initial volume, so our 20 milliliters, times the 0.010 moles per liter of the calcium chloride, because that's where we got our calcium. Remember, it came from the calcium chloride. And we're going to divide that by our new volume. So really, we're looking at how many moles do we have and in that final new volume. So if you look at it, you can see that the new concentration is actually half of the old one, because it makes sense, because we just doubled the volume. Now we're going to look at the sulfate. The sulfate came from the sodium sulfate. So in this case, we're going to use the concentration and the volume of the sodium sulfate at the beginning But this time we're going to divide by our new volume, which is 40 milliliters. And once again, you're going to see a change in the concentration. So our new concentrations are lower than our original ones because we've increased the amount of volume that we had. We need to use these two new values, and we're going to set up our trial KSP expression. So this really is your reaction quotient. This is Q. So we leave out the solid in the denominator because solids are not included in our solubility constant expression. So plugging in the numbers, now we have our trial KSP. So your next job is we need to compare it. We need to see is it greater, less than, or equal to the real value. Now you looked up the value, and if you remember, it was 1.7. So what we find is 7.1, which we find is actually less than our real one. So our Q will have no precipitate because it is indeed less than. So no precipitate because in fact it did not go far enough. It is unsaturated. So there is your first one. The second example is very similar. In this one, we have two solutions that we are combining. They are not in equal amounts this time, so we do need to consider that we need to find the new concentrations of both of them. So first of all, do your balanced chemical equation. You'll find that silver chromate is not in your solubility tables, and whenever that happens, obviously, I will have to give you that information, and that would be your possible precipitate. If you look up the KSP, this one is a very tiny one with 10 to the negative 12 value, so quite insoluble. So we just need to see if we have the adequate concentrations and volumes in order to cause a precipitate to form. So we need to look at our net ionic equation, which if we just look at the silver and the chromate, will come out to 2 silver ions for every 1 chromate ion in your dissociation. Now considering that, we're going to look at the silver ion and the chromate ion. We're going to find the new concentrations of both. So combining our volumes, we now know we have 100 milliliters total. We're going to use our dilution formula. Concentration volume of the initial equals the concentration times volume of the final. So moles are not changing. For the silver. Now in the silver one, we know that when it dissociates from the original compound, which is silver nitrate, that's 1 to 1. So we can do a straight C1V1 equals C2V2. Our initial concentration times volume divided by our new total of 100 milliliters or 0.10 liters. So that gives us 1.0 times 10 to the negative 3 moles per liter for the new concentration. Okay, obviously it's going to be less because we've added more solvent. We have a lot more solution now. The chromate at the same time is going to be the same as, so we're going to look at the original concentration. The chromate came from sodium chromate, and we only had 1 for every one of the original molecules. So concentration times volume divided by our new volume of 100 milliliters gives us our new concentration, 1.5 times 10 to the negative 4. Now that we have those, we can set up our KSP value. We're going to compare the trial. So we're actually determining Q, otherwise known as the trial KSP. So setting that up, notice that there is no denominator. We have our powers according to the net ionic equation. Plugging in your values, we now have our trial KSP. Okay, if you remember, our real KSP is 1.2 times 10 to the negative 12, significantly smaller. So in this case, Q is larger. What that means is that we're definitely have a precipitate because it went so much further into the products that we have a supersaturated solution. Therefore, you will indeed see a precipitate. So at this point, I recommend you working through the problems on the worksheet, at the back of the worksheet. The answers to those are posted on Google Classroom. You can take a look at those. There's photos of the written out ones. A couple of things to take warning on. In some cases, you need to watch that original concentration because in some cases, the ratio may not be a 1-to-1 for your new ions. So watch out for that in the problems. We will take them up when I return, but I wish you all the best. Your textbook has excellent outlines of the questions, so you can also use those as a reference. So good luck.